Okay, so you should be able to see the screen now. Again, yesterday or last class, we talked about calculating E cell, or the voltage of a cell, using the voltage of the, I want to say anode and cathode, but we haven't learned those words yet, which is kind of what we're going to look at today. So I introduced this last day. Again, that would be Sunday. Showed you just a quick picture of this, but never really explained anything. So there are two types of, there's lots of different types of cells and batteries, but there's two general types in Chemistry 1121. There's the galvanic cells. Oops, sorry. Oh, I hope it doesn't do this to me. Okay, hold on. I got to get my pen working. This is going to drive me crazy. Just give me 1 second to get my pen working. I'll close it. It's too early in the class to not have my pen work. Okay, let's try this again. There we go. Okay, so sorry. Let me share my screen again too. I always forget to do that. So there's two types of cells. There's galvanic. These are the ones that produce electricity, and electrolytic. These are the ones that require electricity. So these are the most important. In terms of like drawing, these are spontaneous. So if you remember last day, we talked about the waterfall method and all that. The galvanic cells are the ones that do that. They create electricity. Electrolytic cells are ones that require electricity. So this is a type of electrochemical reaction where you put in energy, kind of like plugging in your phone. And we'll talk a little bit about electrolytic at the end of today. So here's a picture of a classic galvanic cell, and it's kind of similar to what you guys did in your lab, somewhat similar. The only difference in your lab is you guys used what's called not a salt bridge, you used a porous cup. And that's just because it's a lot easier in your lab to use a salt bridge. Harold is a rechargeable battery, galvanic and electrolytic. You can think of it like that. I don't think technically people would call it that. But in terms of like the chemical processes, yeah, like your cell phone battery, when it's powered on, it's in your pocket, you're using Uber or checking, whatever, social media, it's using the energy from the battery. And then when you plug it in at night, it's taking energy from the wall, from, your home, and putting it back into that battery. So I don't know if like a battery expert would technically say galvanic / electrolytic, but the reactions are there and the concepts are there. So today we're going to look at this. We're going to study this type of cell. We're going to kind of practice this. We're going to actually, the only real thing that you need to know from this section is we're going to sketch this. We're going to fill in the blanks. And I'll kind of explain what I mean. So first things first, one thing to remember for a galvanic cell, and you only have to sketch or worry about galvanic cells, is they're spontaneous. That means the E cell is always positive. So if I gave you, and I'm kind of wish these slides were in a different order because I'd like to explain the anode and the cathode in them, but I'll do that in a minute. But if I hook up these chemicals in a cell, it could be like you did in your last lab, you had that glass and a porous kind of ceramic cup that you put on the inside. Really what this question is saying is, which of these chemicals will be reduced, which of these will be oxidized, meaning I'm going to have to flip one of these. And this is, again, a spontaneous reaction, very much like that waterfall method I showed you in the class last week or last day. So for a galvanic or spontaneous, you always flip the lowest. Remember, you're trying to make the reaction of these cells positive. So the only way, or the easiest way to make this positive, is to flip the last one, flip the zinc. So we always flip the lowest, and you're going to see a bunch of examples of this today. Okay, so it says which reaction will happen here. Well, this will be my reduction, and this will be my oxidation. And I know it's oxidation because the oxidized reaction is always the lowest, low, low, low. Okay. Now, you guys actually pretty much did this in the lab, but I'll give you a quick rundown of this. And sorry, let me check the chat here. It's Iman, that's a really good question. It's the lowest. It doesn't need to be negative. It's just the lowest number is the one that flips. Always. Now, this is always true for a galvanic cell or a spontaneous cell, but that's all we're really looking at here. We're not going to be looking at electrolytic cells. So yeah, everybody make sure you make note of that. It doesn't have to be negative. It's the lowest or smallest number. And the reason for that is it's going to give you the most positive answer by flipping the lowest. Okay, so in order for the cell to actually be a cell, you need to collect or connect it to wires. But you just can't throw wires into a beaker and let it happen. You need electrodes. Electrodes give you a way to connect a wire to metal to put it in the solution. So electrodes are metals like zinc and copper, and it's where our half reactions take place. Sorry about that. I just dropped a plate. Electrodes, these are the solid strips connected to the wire. It's where the half reactions take place. Typically, and actually, I shouldn't say typically, in this case, always metals. Now, this is really important. And you know, I'm going to teach you two words right now that is, I don't want to say important for the final. It's just important for your understanding. I want to explain to you the names that we give these electrodes, and you probably heard about this in the lab: anode and cathode. Very important words. Okay, sorry, I'm just writing something down. So in one half reaction, in one part of the cell, the zinc is being oxidized. Okay, the way that's happening is it's losing electrons. Oxidation, and make a note of this, oxidation always happens at the anode, and in CH1121, it's basically the guy on the left. Okay, zinc in this case is called the anode, and the name for anode is where oxidation occurs. Make sure you write, like, you have to know that the oxidation is at the anode. If you're wondering where the name anode comes from, and I won't get too much into the details, but anode comes from because anions are attracted to it. And I'll talk a bit about that later. Okay, so zinc is the chemical being oxidized. It's losing electrons, and it happens we give it a name called the anode. On the other side, the copper is being reduced. Reduction happens at the cathode. Cations are attracted to the cathode. That's where the name comes from there. And when I was in chemistry, no one ever told me this. Or, well, if they did, I wasn't listening. I never really thought to myself, why would they call one the anode and one the cathode? I kind of just thought it was arbitrary names. But the anode attracts anions, and the electrode attracts, sorry, the cathode attracts cations. It's one of the few times where like something in chemistry kind of makes sense. Yeah, like if you're thinking of a battery or like a connection, the anode is typically positively charged because it's losing electrons. But we don't really talk about positive and negative in chemistry. I think you did in the lab, but that's something they deal with a lot more in physics. But yeah, that's a good question. I'm going pretty quick through this because really the only thing you need to take away is that anode has oxidation. That's on the left. Cathode is reduction. That's on the right. And there's one more thing that you need to know. Wink, wink, wink. And this should make sense. And I'll explain why it makes sense in a second. Electrons in a cell always go from anode to cathode. Always. Now, think about it. If anode is where oxidation happens and the cathode is where reduction happens, logically put that together. We've been talking about redox for a few weeks. Oxidation, the chemical loses electrons. Cathode, the chemical gains electrons. So of course, electrons move from anode to cathode. Again, the anode oxidizes, it's losing the electrons. They go through the wire over to the cathode gains them. So guys, electrons, whoops, I didn't mean to do that, always flow this way. Sorry, the Zoom screen is in the way, but electrons always go from anode to cathode, always. Yeah, so Aman, like again, that's a tough question in chemistry because what's happening is the anode is losing electrons, okay? The anode's losing electrons because it's the oxidation rate reduction. So it's losing a negative charge. So it becomes temporarily positive. And that's why the anode attracts anions, because as it's giving away electrons, it's becoming more and more positive, and we need to balance that out with the anions. That's where the name anode comes from. Again, I wouldn't worry at all about this. There's a private message I didn't see. It says, how can you determine which is the anode and which is the cathode? There's two ways. Follow the flow of electrons. Electrons leave the anode and go to the cathode. And the other way you can do this in the chemistry 1121 is we always put the anode on the left and the cathode on the right. But the true answer to your question is you can tell which is the anode and the cathode based on which is being oxidized and which is being reduced, like follow the flow of electrons. So like this is a good example to that private message I have. It says show the electron movement and ion movement in the cell below. Well, I'm telling you that the anode is here and the cathode is here. So electrons flow from the anode to the cathode. Okay, now remember, the anode is oxidation, the cathode is reduction. So an oxidation reaction is when it loses electrons, and a reduction reaction is when it gains electrons. So here, the silver is attracted. It's going to what we would call plate or be attracted to the silver. Here, the electrons leave the potassium and turn into potassium ion. Again, that's from the half reactions. You'll see a bit more of this in a minute. These half reactions is a little bit easier than this. This is just kind of like a simple example to show you where the ions are moving, but you'll see kind of like, how did I know this in a minute? It's trust me, it's easier than it looks. Oh, I had the picture there anyways. Sorry about that. Okay, now this is not important. Don't worry about this part, but this, if we were a little bit ahead, I would have mentioned this for your labs. What's going on with this thing, right? What is the point of it? Well, this is called, oh, hold on, well, I'll tell you what it's called. It's called the salt bridge. Okay, I'll go back to that slide in a second. This guy in the middle is called the salt bridge. And what it does is it completes the circuit for this. I think about, again, I don't know how many of you are in physics, but if you've done any type of circuitry in physics, think about completing a circuit. You know, you need to have a closed system, I guess we could say, or a closed circuit. The salt bridge keeps the balance of ions. So let me go back and explain what I mean by that. So think of the same reaction before. As electrons leave the zinc ions are going out into the solution, and it's going to happen all the time, over and over and over. On the other side, the copper half cell would run out of copper to react with. So the reaction will stop unless we balance the charges or balance the, or I guess I could say close the circuit. So, and again, guys, you don't need to know this, do not worry, but the purpose of the salt bridge is to keep the charges in balance. You know, as electrons keep leaving this side, it's becoming positively charged and anions are going towards it. But how do we keep a steady supply of anions in the solution? The salt bridge. Cations are attracted to the cathode. How do we keep a steady supply of cations in the salt bridge? Well, we put cations in there. So the salt bridge typically contains a non-reactive solution. You'd like to keep it non-reactive so you don't have anything dangerous or anything happen on the side of something like, it could be sodium chloride. I've seen potassium chloride, or in this case, we have ammonium chloride. Ooh, stinky solution, but a good one. So again, the purpose of this is to kind of close off the circuit, keep the charges balanced. You will not have to worry about this for your final, don't worry. How do I clear my ink? So again, keeps the reaction going, balances charge. All right, let's get into the real stuff, the real details here. Oh, and by the way, this is just a picture of referencing what you used in the lab, so you guys can hopefully get a visual of this. This typically will stop quicker than a salt bridge, but this you should have been, I think, your last lab if you were there, where you used a little cup in a glass. Aman, I'm not sure about your question. Maybe if you could clarify. I'm just going to put an X there because this was just for your lab. You don't need it for your exam. So here we go. Here's our wink wink question of the day. I want you guys to sketch a galvanic cell. Sorry, I'm just checking the chat. I wish it would open easier. Yeah, you can go back and watch it. I think it was the class that we did Sunday, so like a week and a bit ago, Sunday. Again, you're kind of, this is not that for anybody, just kind of ignore what I'm about to say, but you don't worry about bases. You're asking something from weeks ago. But yeah, you can watch the slides again if you can't remember, but we're going to balance in acidic conditions, not basic. Okay, does that make sense? Okay, I'm going to assume silence means good. All right, cool, perfect. Sorry, it just took me a minute to figure out what you were talking about because that was the balancing of half reactions from a while ago. Okay, so this is my wink wink type of question for today. The main question from this section, you know, you guys are going to be given a blank cell like this, and you're going to be expected to very simply label it. And I'm going to show you how it's done. It's way easier than it looks. Okay, so first things first, we need to figure out which is the anode and which is the cathode. And we've already done this. We've done this before because all I need to do is figure out which chemical is being oxidized and which chemical is being reduced. So I'm just writing my half reactions down. I'm balancing them with electrons. We did that already. I don't care about balancing anything. I don't even care about balancing charges. Okay, but I have my half reactions here. If you're wondering where did I get it, I know aluminum is turning into aluminum 3+, so I balance it with 3 electrons. I know lead is turning into lead solid, so I balance that with 2. Again, you do not have to make sure they cancel out. This is not balancing half reactions. All I wanted to do was to see which chemical was oxidized and which chemical was reduced. So, oxidized, reduced. All right, well, I'm going to put my anode on my left. That's how we typically do it. Hint, hint. Cathode on the right. And I'm just going to write what happens. So first things first, for 1 mark, electrons go from anode to cathode. Okay. Second mark, I know that my aluminum is being turned into aluminum 3+. Now, how did I know that? It's right here in my reaction. It's right here. Aluminum is turning into aluminum 3+. Ions. My lead 2+ is turning into lead. And there you go. That's it. Now, you could mention the salt bridge if you wanted to. I personally don't care about it. The way, again, the salt bridge works is the negative charge goes towards the anode, the positive charge goes towards the cathode. But we're going to do some more of these, don't you worry. Let me check the chat.
So I have a question.
Abdul Halim, maybe,
Oh,
you know, 1 second. Maybe, I'm sorry, I'm reading the chat first, but Abdul Halim, I'd say 3 or 4 marks. And then you had someone else had another question?
yes, sir. Is it always the anode on the left and the cathode on the right?
I mean, you can draw it however you want, but for us in this course, we do anode on the left, cathode on the right.
Yeah, okay.
Yep, it just makes it easier to be consistent.
Yes. Thank you.
No problem. You can see in the black writing there, this reaction was balanced. You like, again, you do not need to balance this. You're just trying to see which is oxidized and which is reduced. So, all right, sorry, I'm just seeing what's coming up. Let me do another one for you, and then I'll give you guys one to try. Oh, give me 1 second. Okay, sorry. I have to move a slide. Just hold on 1 second. My slides are out of order here because I just kind of changed some things around. There we go. Okay, sorry, I just had to move this. Sorry, I want to do this one first. Now, this is another kind of good type of question. This is more of a wink type of question.
Can't see the screen.
You can't see the screen, eh? Hold on 1 second. This is kind of like a wink wink thing here. Sometimes you want to check a reaction that doesn't have a metal in it, like, so what, we've checked lead and copper and zinc, but what if you wanted to check the electronegativity of fluorine or something like that, or not platinum, hydrogen or something like that. If you don't have a metal, you use a platinum electrode. Okay, if you do not have a metal, use a platinum electrode. This is more of like a multiple choice type question where I'm not going to get you to sketch this. So actually, this question here, you can ignore it because we would need a platinum electrode. You're not going to have to sketch that, don't worry. But it is good to know, maybe for another type of question, if you don't have a solid electrode, like if you're dealing with all gases or liquids or all aqueous, you need to use platinum. Okay, sorry. So yeah, let's do this example. This is a good one. Draw the galvanic cell for this reaction. Label the anode, cathode, electron flow through the wire and in the salt bridge. Okay, so you'll notice, guys, I separated this into 2 slides so I could actually draw on this. I've kind of modified the notes a little bit over the last couple days to kind of simplify this. Well, just to see, I'm just going to see how you guys are feeling. Maybe take a minute and try this one. Just take, you only need 2 minutes because you're only going to be drawing some arrows. Try this one, and then we'll go through the answer. Okay, so I'll be back in a couple of minutes, maybe 2 minutes. Sorry, guys, I just had to check something. Keep working. Just had a question in the chat there. The second one is definitely supposed to have Pb2 plus inside them on. The cathode side should have Pb2 plus. And yes, label the bridge. Hey, okay, so you guys keep working. The NO3, oops, can kind of come from anywhere. What I mean is your salt bridge just has to have a salt in it, and it's kind of whatever salt you want. We can use NH4 and Cl minus. We could use Na plus and Cl minus, whatever salts you want to use. In the previous example, we used chlorine. So yeah, it really doesn't matter what you put in the salt bridge. Maybe the easiest thing for you guys to put in would be table salts, right? So, because a salt is a positive and a negative chemical. So you could just put any type of salt in there. Yes, Abdul Halim, yes. Guys, you cannot put charges. That's a good question. You cannot put charges on this. This is always the solid chemical. This is your electrode. It has to be solid. Like the reason it's a square is because it's a piece of metal. It's a piece of solid. So always put your solids here and your ions here. Ions are in the beakers in the solution. Solids are the sticks, you know, the rectangles, I guess. Does that make sense, Abdulhalim? Because that might really help you. Yeah, okay. That's good. I'm glad you asked me that question because that's good. Okay, so let's fill in our labels here. And guys, I hope you were listening. Aman's question was good as well. Like, where did these chemicals come from? These are just a cation and anion that I picked to put in the salt bridge. You guys can put anything in there you want. And honestly, maybe the easiest would be table salt, right? It's anything that has a positive or negative charge. Okay, so filling in my arrows, electrons go from left to right because, again, we have anode and we have cathode. Okay, the iron is getting oxidized, so this arrow goes this way. Now, how did I know that? Well, guys, look, like literally my chemical reaction arrow goes from iron solid to iron 2 plus. So I do the same thing here. The cobalt does the same thing. Look, the cobalt turns into cobalt solid. Let the reaction guide you on how you draw your arrows. Anions are attracted to the anode, cations are attracted to the cathode. We are done. It looks harder than it is, but it is actually pretty easy, Marks. Yes, exactly. Like remember, guys, cations go towards cathode, anions go towards anode. That's literally the definition of them. Cations, cathode, anions, anode. All right, cool. We got one more. I think I got about 6 slides left. It shouldn't take me too long. How's everybody doing with that? Any questions on drawing cells? There are some practice worksheets for this. I would definitely try them. I think it was Abdulhalim asked, what is this worth? It's worth, maybe 3 or 4 marks. I think, I can't remember now. I guess I could look, couldn't I? It's only a couple of marks. All right, no questions. One last part and we are finished. There's about 6 slides left, and there is unfortunately one last calculation we're going to do. We're going to end the year off, end our wonderful chemistry class off with a calculation. Personally, my favorite part of chemistry. I don't know about you guys. So a calculation. One of the coolest parts about electrochemistry, and this is kind of related to galvanic cells, except in this case, it's an electrolytic cell. Don't worry, you're not going to have to draw this. But this is one of the coolest parts of chemistry. We can do something called electroplating. Electroplating is a method used to plate, meaning put one chemical over another, using electrochemistry. So sometimes you can get like silver plated jewelry. It's not pure silver, it's been plated. You can get gold plated or silver plated like cutlery, forks and knives. This is all used, or electroplating is what does this. This is another way to prevent against corrosion. You could take a metal that easily corrodes and plate another metal on it. And I can actually just explain it with this last picture. In this side of this cell, all of this cobalt is sticking onto the cobalt metal. So all of these ions are covering this metal. So we're plating the cobalt on itself. The reason electroplating is different is you can typically plate on one metal, or when I say plate, I mean deposit one metal onto another metal. The only problem with this is it takes electricity. So we're going to end on a beautiful calculation. It's going to look a little scary, but it's really not too bad. Give me 10 minutes or so and we should be good. Although I might give you guys a practice one to try. First things, we need to think about some terms. When you're plating these chemicals, you need to consider charge and current because you are going to use electricity to do this. You can think about the amount of water in a river when you think of charge. Charge is the total amount of water that passes by you in a river. Now, you can have a river that goes fast. You can have a river that goes slow. The speed of that water we would call the current. So there's a formula based on that where you can calculate the charge that's produced in a cell using this formula called QUIT, Q equals IT. It's obviously in your data book. Okay, this formula Q equals IT is pretty straightforward, 3 variables, and I have an example down here. This is not the example I would waste my time on. This is just getting you guys prepped. How much charge, Q, is produced when a current of 2.3 amps. We always measure current in amps and charge with C or coulombs. How much charge is produced when a current of 2.3 amps is running for 1.2 seconds? Or sorry, 120 seconds. Now think about this back to the river. The charge is how much water flows by you. The current is the speed of the water. And you can think of, again, the water, that's electrons, of course. So to figure out the charge, I say, well, how fast is the current? And I multiply it by time, and I will get my charge. So Q is I times T, 2.3 amps times 120 seconds. We would get an overall charge of 276. This is all getting us ready for another problem, by the way. 276, wow, Abdullah, thank you. You guys might have done a bit of this in physics, but the next part of this you definitely haven't done in physics. I got one more thing to show you, and then we're going to put it all together. What does charge and amps, what does this have to do with chemistry, right? It wouldn't be a chemistry question unless there were moles, right? So once you know the charge, you can actually calculate the moles using this formula, obviously in your data booklet. Moles is equal to Q, your charge, over F, a constant. This is, of course, in your data book. Right, so a little easy example on the bottom to get us warmed up. How many moles of electrons are produced if you have 5,000 coulombs of charge? Well, Q is my charge. I divide it by F, and I get my answer here in moles. All right, again, this is all going quick because I'm trying to set up the last part. I think I only have 2 or 3 slides left. So putting it all together, there's 2 slides left, guys, and we are done this whole course. Okay, putting it all together. How do we do this problem? Okay, so let me show you one, and then I'll see if you guys are, awake at 4:15 on a Tuesday afternoon. What mass of calcium would be produced when 1.5 amps would run for 2.50 hours? Well, first of all, let me make this a little easier on you, and I'll make it like it is on your final exam. 2.5 hours, this would be 9,000 seconds. Okay, so 2.5 hours would be 9,000 seconds. You guys don't need to worry about converting the time on your final. You will obviously be given it in seconds if you need it. Okay, so let's think about what I know. I know I'm dealing with calcium. I know I have amp, so I have I, and I have time. So I know I have I, and I know I have T. But the question is, what is the mass? Well, step number one, calculate the charge. And the reason we do that is because with the charge, we can actually calculate coulombs, and we can use that to find my moles of electrons. Honestly, guys, if you can get through the steps 1 and 2, this is all chemistry 1120. So, okay, step 1, Q is equal to my amps times my time. So it's 1.5 amps times 9,000 seconds. I get my charge. No problem. Now I want to find the moles of electrons. So moles of electrons is Q over F. Okay. So my Q, 1.35 times 10 to the 4 coulombs. Now remember, F is a constant. Okay, equals 0.139 moles. That's step 2. Now this is all review, right? What do you do if you have moles? Well, and you guys did this in acid and base chemistry. You did this in chemistry 1120. Once I know the moles of something, I can find the moles of anything. Okay, so I'm looking for my moles of calcium. So step 3, I'm going to find my moles of calcium by multiplying it by my good old mole ratio. Now, on the test number 2, I had, I'd say, about 80% or more of the students get the mole ratio correct in the titration question. Like really, really well done. For anybody who didn't get that right in the titration, there's 2 questions now where you're going to need a mole ratio. Again, why is it 1 over 2? Well, because I'm looking for calcium and I have electrons. It's 1 over 2. So I get my moles of calcium, and we're back to the most classic chemistry equation of all time. Mass equals moles times molar mass. So I multiply my moles by the molar mass, and I am done. So if I let the current run for 2.5 hours, I would obtain 2.8 grams of calcium. Sorry, I'm just reading some questions here. Sir, is it always mole for aqueous, same as mole for solid? Yeah, actually, yeah. In a half reaction, yes. In any of the half reactions, we'll see. But I mean, I didn't care about the ion at all. I only cared about my electrons and my calcium. Okay, we're almost done because it's 4:15. Oh, no, no, no. You definitely need step 3. Step 3 is the most important step. Because I'm not talking about ions. I'm talking about these electrons. It's 1 over 2. 1 over 2. You definitely need step 3. All right. Okay, here's the last one. This is it. This is the end of the course. And this will be my last wink wink of today. Guys, there's been 2 major winks today. So we've done a lot today. It's the end of the year. There was a little bit to do. If I could, tell you, 2 winks, 2 things to consider, it would be something like this question. So I don't know what number slide this is, but it's this question. Basically labeling a cell. And then this question. And guys, by the way, this question is the exact same as this question. It's just we're going to do the steps in reverse. Aman, did the whole mole ratio make sense to you? Is that clear? This is the last wink wink of the semester, basically. All right, cool. Well, guys, I was going to give you a minute to try this one, but I think I'm going to do this for you because, again, this is our last kind of most important question. Again, guys, it is the same as this question, except what we're going to do is we're going to go in reverse. So, step number 1. I'm trying to think, do I want to write this down or do I just want to go through the steps? I'll go through the steps because this is probably would be hard to fit this all on the slide. So step number 1. Now, guys, think about what this is saying. This is asking for time and it's giving me the mass of lithium. So really think about how you're going to make a plan for this. It's also giving me amps. But in order to find time, I need to know Q. So my goal here is to find the amount of charge in that 1 gram of lithium. So I'm literally going backwards through my steps, right? So step number 1, my moles of lithium equals mass over molar mass, 1 gram over 6.941. Now, remember, guys, where did I get this math? Just straight up look up on your periodic table. Same thing back on this slide. Sorry for the mess. Where did I get this molar mass? Straight from the periodic table. You don't have to calculate it, because it's always going to be for a pure metal. So I just go find calcium on the periodic table. Here I find lithium. All right, I get my moles. Next step. Now that I know the moles of lithium, this lithium, I can find the moles of this. Now this is an easy one because my moles are 1 to 1. So like Aman mentioned in the last slide, oh, we can skip this step. If they're 1 to 1, you could skip this step. Step number 2 is to find my moles of electrons. This is just my mole ratio, 1 and 1. Okay, honestly, guys, step 1 and step 2, that's review from Chemistry 1120. Even though we didn't talk about electrons, calculating moles and using mole ratio, easy. But now I want to find Q so that I can find time. Well, if you know your moles of electrons, and of course you know Faraday's constant, remember this is a constant, you can multiply them together to get Q. And then the last step, find time. So take that Q and divide it by your amps. Amps were, remember, back in the beginning of the question. So I would take my Q 1.39 times 10 to the 4 coulombs and divide it by my amps. And I would end up getting 7.94 times 10 to the 3 seconds, or what your calculators will probably say is 7940 seconds, which is how I would probably write this down if I was going to be normal. Abdullah, remember at the beginning of the year, I said molar mass would be given in the question. It will be given in any question where you have to calculate it. But I will warn you that in this last question, you will have to look it up. No calculations required. You just have to look at lithium on your periodic table. that's the same as giving it to you, because there's no calculations. But for every other question in this course, molar mass will be given to you. You will have to look. Dom, sorry, you have to, but it's easy. I mean, at least you don't have to calculate it. Okay, guys, I mean, that's it. That's the finale. A couple things I'll mention is, well, I think we're all going to see each other again for a few reasons. One, I have, or I'm in the exam room with you. Two, I'm going to be offering 2 different tutorials for your final exam. So let me stop sharing here. I'm going to offer a tutorial on, hold on now. I'm just going to share my new screen here. I'm going to offer a tutorial on Thursday afternoon, and I'll pick the time later, and Saturday evening. Now, again, I know some of you guys have a stats exam on Saturday in the afternoon. So you don't have to come on Saturday evening, but Thursday you might want to come afternoon. You can join either. You can join Thursday or you can join Saturday. I'm getting questions about Unit 6 in the chat, which is fine. Remember, that's a self-guided unit, and I can talk more about this in the tutorial. Unit 6 I uploaded over the weekend. It's not what you think it is. It's very short, self-guided. And the reason it's self-guided is because if you are in health science, you do this. If you are in engineering or any other program, you do this. They are the same amount of information, but basically what it is, it's about some special chemicals. So the medical science students, and again, I can't separate you, so this is something you can read on your own. The medical science students will talk about fullerene and phosphorus. The engineering students will talk about metals and alloys. And here, I'm going to just tell you something that's going to make you guys feel really, really good about this. And I will talk about this in the tutorial. I have uploaded a final exam review, and we'll do more of this in the tutorials. This is like, this whole document is one gigantic wink, wink, wink of everything in this course, of things you should study. You know, it kind of cuts out all the extra information and tells you all, you know, the things you should know. And if you go down to chapter 6, which is here, basically, guys, you can, if you are a health science student, you need to look at 4 slides. If you are a engineering student, you need to look at 5 slides. I'm sorry, there's 1 extra for you guys. That's it. That you just need to look at 4 and 5 slides respectively. So again, the reason we didn't do it in class is because it depends if you're health science or engineering, but I can take time in the tutorial and actually help read, you know, we're basically out of time now, but maybe on Thursday or Saturday, if you guys wanted me to go over the 5 slides or the 4 slides, like you read them and you don't understand, I can do that for you. So Harold, you can join either. I highly recommend you join both. And if you can't join either, don't forget I will be putting them up on YouTube. And Aman, I think I answered your question there about chapter 6. There are 4 slides that you guys have to kind of do on your own if you're health science, and 5 if you're engineering. Oh, oh, I won't forget to record. I'll try to do as much as I can in Thursday, and I'll leave kind of Saturday's tutorial for the panicked students, you know, because Saturday night, I don't want to teach too much because you guys should kind of be studying and reviewing. But yeah, all right, guys. I mean, I'm done for today. Aman, you can just ask me what you're confused about. I got time. Thank you. It was so good to have you guys as an instructor. The last classes have been uploaded on YouTube. Thank you all for the semester. You guys are such a good class. I'll say or talk to you again in the tutorial if you can make it. But you guys have been a wonderful class in this trying time. Okay, so see you guys, you can leave. No, Aman, so in the final, when you're doing your exam, you do the section that's related to you. I will, sir. I will, Harold. Thank you very much. So Aman, if you're health science, you do the health science part. If you're engineering, you do the engineering part. Yes, I'll miss you guys too. Have a nice day, everybody. Sorry for the long one. I'll see you later. See you on Thursday, I hope. All right, bye. Nor 1:30. I'll start it at 1:30. Is that a good time for you?
Yes, sir, no problem.
Okay, perfect. I'll be posting all this information on D2L anyways. All right, thanks, Noor.
Thank you so much, sir.
Thanks.
Take care. Stay
Thank you.
safe.
Yes, you too. Thank you. Bye-bye.